Morning. Today we are discussing states of matter. This is the fifth chapter of class 11 chemistry. States of matter contains three types of physical states, that is gas, liquids and solids. Gases have no fixed shape and no fixed volume. They can attain the shape of the container in which they are kept. They are highly compressible and they can flow easily. While liquids, they do not have the fixed shape but have the fixed volume. They are not easily compressible, they flow easily. While solids have fixed volume and fixed shape, they are not compressible, they are rigid. Now you can see the structures of solid, liquid and gas. They can be easily converted into one form to another. When solids are heated, they convert into liquid and after that they convert into gas. We can also convert solid into gas by the process sublimation, and gas can be converted into solid by the same process, that is sublimation. While solid converts into liquid, that process is known as fusion or melting, and liquid converts into solid, that process is known as freezing. While liquid converts into gas, this process is known as vaporization, and condensation of gas into the liquid form, that is condensation. Now, intermolecular forces of attraction. There are intermolecular force of attractive forces are present in the molecule. They hold atoms together in a molecule. Now, intermolecular force versus intramolecular forces. Intermolecular forces are the weak forces in comparison to intramolecular forces. As we know, 41 kilojoule energy is required to vaporize 1 mole of water, because intermolecular force of attraction is present between the two molecules of water, while to break 1 mole of OH bond present in the water, that is intramolecular force, that requires 930 kilojoule energy to break the bond. Intermolecular forces generally known as Vander Waal forces, while the intramolecular forces includes bonds, angles and dihedrals. Types of intermolecular forces. First, dispersion force or London force. London forces are known as the dispersion forces, and that take place between the non-polar molecules. These are the temporary forces, and these are the weakest intermolecular forces of attraction. This exists, or this is created when for a fraction of time, when non-polar molecule contains the polarity, and it makes the another adjacent atom to become polar. Dipole-dipole forces. Dipole-dipole forces are the attractive forces between the positive end of one polar molecule and the negative end of another polar molecule. Dipole-dipole forces have the strength of 5 kilojoule to 20 kilojoule per mole. They are also weaker forces but stronger than the dispersion forces, and they are weaker than ionic or covalent bonds. Now, induced dipole forces. Ion-induced dipole forces. An ion-induced dipole attraction is a weak attraction that results when the approach of an ion induces a dipole in an atom or in a non-polar molecule by disturbing the arrangement of electrons in the non-polar species. Dipole-induced dipole forces. A dipole-induced dipole attraction is a weak attraction that results when a polar molecule induces a dipole in an atom or in a non-polar molecule by disturbing the arrangement of electrons in a non-polar species. Hydrogen bond. Hydrogen bond is a special type of dipole-dipole interaction. It is present between the hydrogen and more electronegative atoms like fluorine, oxygen and nitrogen. This is the strongest force among all the Van der Waal forces. Now gas laws. Boyle's law. According to Boyle's law, at constant temperature, the pressure of a fixed amount of gas varies inversely with its volume. You can see in the graph, that is P inversely proportional to V, and PV is equal to constant. Now Charles' law. Charles' law expresses the relation between temperature and volume. According to Charles' law, volume of the gas is directly proportional to the absolute temperature at constant pressure. Now Gay-Lussac's law. Gay-Lussac's law states that at constant volume, pressure of a fixed amount of gas varies with the temperature. That is, P is directly proportional to T. Now Avogadro's law. It states that equal volumes of all the gases under the same conditions of temperature and pressure contain equal number of molecules. That is, V is directly proportional to N. Ideal gas equation. Ideal gas equation is a relation between four variables and it describes the state of any gas. Therefore, it is also called equation of state. That is, PV is equal to nRT. You can see how we can derive this. Dalton's law of partial pressure. According to this law, the total pressure exerted by the mixture of non-reactive gases is equal to the sum of partial pressures of the individual gases. Kinetic molecular theory of gases. The most important assumptions of the kinetic molecular theory of gases: a gas is composed of particles in constant motion. Second, the average kinetic energy depends on temperature. The higher the temperature, the higher kinetic energy, and the faster the molecules are moving. Next, compared to the space through which they travel, the particles that make up the gas are so small that their volume can be ignored. The individual particles are neither attracted to one another nor do they repel one another. When particles collide with one another, they bounce rather than stick. These collisions are elastic. If one particle gains kinetic energy, another loses kinetic energy, so that the average energy remains constant. Now, behavior of real gases means deviation from the ideal gas behavior. A gas which obeys the gas laws and the gas equation PV is equal to nRT at all temperature and pressure is said to be an ideal gas. The molecules of ideal gas are assumed to be volumeless points and no attractive forces present between one another. But actually, no real gas strictly obeys the gas equation at all temperatures and pressures. Deviations from ideal behavior are observed particularly at high pressures or low temperatures. The deviation from ideal behavior is expressed by introducing a factor, that is Z. It is known as compressibility factor in the ideal gas equation. Z may be represented as PV upon nRT. In case of ideal gas, PV is equal to nRT, so Z equal to 1. But in the real gas situation, Z is not equal to 1. It is either greater than 1 or lesser than 1. If Z is less than 1, then it shows negative deviation. It shows the gas is more compressible than the expected behavior, ideal behavior. While if Z is greater than 1, it is showing the positive deviation. It shows that the gas is less compressible than expected from the ideal behavior. Causes of deviation from ideal behavior. The causes of deviation from ideal behavior may be due to the following two assumptions of kinetic theory of gases. These are: the volume occupied by the gas molecules is negligibly small as compared to the volume occupied by the gas. Second, the force of attraction present between the gas molecules are negligible. Van der Waal equation. Atoms and molecules are never truly ideal because they all interact with other gas particles. Weak attractions between separate gas particles are known as intermolecular attractions or Van der Waal forces. After the chemist who proposed a correction to the ideal gas law to calculate pressure of a real gas, Van der Waal proposed that ideal gas equation could be corrected for real behavior by subtracting the effective gas particle volume from the volume of the container and by correcting for intermolecular force of attraction. Now you can see PV is equal to nRT is corrected. P plus attractive forces, V minus gas volume of the gas molecules, that is equal to nRT. And we can write P plus n square A upon V square, V minus nB, that is equal to nRT. This is known as Van der Waals gas equation, and this is used for the real gases. Properties of liquids. Vapor pressure. The pressure exerted by the vapors in equilibrium with liquids formed to the same substances is known as vapor pressure of the liquid. Now surface tension. Surface tension is the force acting per unit length perpendicular to the line drawn onto the surface of the liquid. Viscosity. Viscosity of a liquid is a measure of resistance to flow. It is related to intermolecular force of attraction. Stronger these forces, greater is the viscosity. Now, thank you.